Welcome to the deep dive. Today, we're going to pull back the curtain on something pretty fundamental to keeping aircraft flying, removing and replacing their engines.
That's right.
You shared a really comprehensive chapter on this, and, well, we've kind of boiled it down to the essentials for everyone listening.
Yeah, exactly. Your material covers a huge amount, from the basic reasons why an engine might need a swap, all the way through the nitty-gritty steps for both piston types and turbines, and crucially, how to keep them in good shape when they're not actually flying.
Okay, so our goal today is really to give everyone a clear picture of this whole process. We want to hit the why and the how of engine changes.
Right.
Focusing on the key procedures, the things you really need to consider, without getting totally bogged down in, super technical jargon.
Yeah, aiming for those aha moments.
Exactly. Those moments that really shine a light on this pretty critical bit of aviation maintenance. Okay, let's dive in. So, what are the main reasons you'd actually need to pull an aircraft engine?
Well, there's several big ones. One of the most basic is just reaching the end of its life,
Its lifespan.
Yeah, its designated lifespan. Manufacturers set up what they call a time before overhaul, or TBO.
TBO, right. I've heard that term.
It's based on all the stresses and strains an engine goes through. And for some really critical parts, especially in those high-powered turbine engines.
Like the blades.
Exactly, like turbine blades. The FAA actually mandates specific replacement times because the forces and temperatures are just extreme. Even tiny cracks can spread super fast. That's why those schedules are so strict.
Okay, so these aren't just, suggested numbers. They're vital for planning maintenance way ahead, right? Affecting schedules, safety.
Absolutely. It's all about being proactive. That's aviation maintenance for you.
Totally. So what else? What other things force an engine change?
Well, another major one is a sudden stoppage or a propeller strike.
Sudden stoppage. What exactly qualifies as sudden?
Good question. It's defined as the engine going from its operating speed down to 0 RPM in less than one full turn of the propeller.
Wow. Less than one turn?
Yeah. Think about maybe a landing gear collapsing on landing or the plane nosing over.
Ouch.
Yeah, ouch is right. Those kinds of sudden impacts can cause serious internal damage.
Mm-hmm.
Cracked gears in the reduction gearbox. Maybe the crankshaft gets knocked out of alignment, damaged bearings.
So in that case?
In those cases, the engine pretty much always needs to be either swapped out completely or at the very least taken apart for a really thorough inspection following the manufacturer's instructions to the letter.
That sounds intense. And a propeller strike? Similar consequences?
Yeah, a prop strike, even if it happens at a fairly low RPM, can cause a sudden drop in engine speed. And even if the engine seems to run okay afterwards, there's still a real risk of hidden damage inside, especially to things like the crankshaft counterweights. So the first step is always a detailed external check: the engine mount, the crankcase itself, the nose section.
Looking for cracks or bends.
Exactly. Any visible damage that you can't fix right there usually means the engine has to come off.
Okay, but how do you find that hidden damage after a pop strike or a sudden stop? You can't just eyeball the inside, right?
You can't.
Yeah.
That's where checking the oil system very carefully comes in. Mechanics will pull the oil screens, the drain plugs.
Drain the oil.
Drain all the oil, yeah. And then painstakingly look for any metal bits.
Metal particles.
Right. If you find big chunks of metal, that's pretty obvious. Something major, let go inside, engine comes out.
Makes sense.
But even finding finer metal filings, that might mean you need to dig deeper, do a more involved inspection. And here's an interesting point. Even if the initial ground run seems okay, runs smooth, makes power, you absolutely have to do another oil check after it's run for a bit. Finding metal, especially in the oil screens, often points directly to a bearing problem.
Okay, so metal in the oil is a big red flag.
Yeah.
But what if the bits are tiny, like microscopic?
Yeah. That's where you get into more advanced stuff, like spectrometric oil analysis programs. SAP, they call it.
SOAP, like washing the engine.
Not quite. You take an oil sample, send it to a lab.
Okay.
And they can measure tiny amounts of different metals down to parts per million. Now, all engines shed some wear metals over time. That's normal.
Right, just friction.
Exactly.
Yeah.
But its OAP looks for spikes. A sudden jump in, say, copper or iron concentration, could be an early warning that a specific part is wearing out fast or about to fail.
So it's like a blood test for the engine.
That's a great analogy. Yeah, it'd find problems you just can't see. Think of the cost savings, too. Catch a bearing going bad with an oil test versus
like catastrophic failure midair.
Precisely.
Yeah.
It's predictive maintenance in action. Safer, cheaper in the long run. Works for turbines and piston engines both.
And turbines have their own monitoring too, right?
Oh, absolutely. Turbine engines usually have quite sophisticated condition monitoring programs. They track all sorts of engine parameters, sometimes daily.
Like temperatures, pressures.
Temperatures, pressures, vibrations, speeds, fuel flow.
Yeah. By analyzing trends in that data over time, engineers can spot subtle shifts that might indicate internal deterioration starting. Allows them to plan maintenance before a major issue grounds the plane.
Makes sense. So beyond these sudden events and wear issues, what other, maybe more operational problems can lead to pulling an engine?
Well, there are a few others. Excessive vibration is a big one, especially in turbines.
Right.
That often signals something's unbalanced or damaged internally. In piston engines, things like persistent backfiring or misfiring could point to valve train problems or other mechanical issues.
Right.
For turbines, consistently operating outside normal limits, or if a critical part hits its life limit, that's cause for removal. And finally, just a significant unfixable loss of power.
Low power output.
Yeah. Could be low compression in a piston engine, or maybe internal damage in a turbine. Either way, if you can't fix it, you often have to swap the engine. Okay, that covers the why really well. Let's shift gears now to the how, the process itself. You mentioned preparing the replacement engine. Tell us about this QECA thing, quick engine change assembly.
Ah, the QECA. Yeah, it's a really smart idea for efficiency, especially in commercial airlines using turbine engines.
So big jets, mostly.
Mostly, yeah. Basically, it's a complete engine package. The engine itself, plus all its essential accessories, all pre-assembled and tested together as one unit.
Like a plug-and-play engine?
Sort of.
Yeah.
It makes engine swaps much, much faster, minimizes downtime for the airline. Now, for smaller planes with piston engines, where swaps might be less frequent,
Yeah.
they might use engines that are maybe partly built up or even still in their storage crates, and they assemble them just when needed. Not quite the same standardized package deal.
Got it. So QECA is all about speed for the big guys. What's involved in actually building up one of these QECAs, roughly speaking?
Well, we won't get into this super specific step-by-step here. The maintenance manuals are king for that. But the key idea is understanding how all the bits connect. A QECA fits inside the engine nacelle. That's the streamlined pod hanging off the wing.
Great. The housing.
Yeah. And the nacelle itself is often thought of in two parts. The wing nacelle, which is kind of fixed to the wing strider, and the engine nacelle, which is the removable unit containing the QECA. The wing part usually holds the fixed lines and controls for things like oil, fuel, hydraulics.
And the engine controls themselves.
Exactly. All the connections run through there.
And inside that nacelle, there's a really critical safety feature, isn't there? The firewall.
Oh, absolutely critical. The firewall is usually the bulkhead furthest forward in the engine nacelle. And unlike other bulkheads, it's made of special fire-resistant materials.
Like steel or titanium?
Often stainless steel, titanium alloys, yeah. Things that can handle intense heat for a decent amount of time. Its main job, obviously, is to contain an engine fire within the nacelle.
Stop it spreading to the wing or fuselage. Gives you time. Exactly. Buys crucial time. But it also does double duty as a mounting point for various bits and pieces, and it's the main place where all those fluid lines, electrical wires, and control linkages pass through from the engine to the aircraft.
So it's a connection point, too.
A major connection and disconnection point. And keeping it properly sealed, any unused openings plugged up, is vital for its fire containment job. You can't overstate that.
Makes total sense.
Yeah.
Safety first. Now, what about an engine that's been sitting on a shelf for a while, in storage? You can't just grab it and bolt it on, can you?
Definitely not. A stored engine and any accessory stored with it needs a really careful, methodical depreservation and inspection process.
Depreservation. Sounds fancy.
Well, no, it just means getting it ready after storage if it's in one of those pressurized metal cans.
Yeah.
First thing is you slowly bleed off that pressure, carefully. Then, whether it's a metal can or a wooden crate, you open it up, take off the outer wrappings, pull out the desiccant bag.
The little moisture absorbers. Right, those silica gel packets. And the humidity indicator card that tells you if it got damp inside. Any accessories stored separately get laid out for their own check, too.
Okay, so it's like unwrapping a very expensive, very important present carefully. What next once it's out?
Once you've got it securely on a maintenance stand, you start taking off all the covers they use to seal it up, caps on the breathers, plugs in the exhaust, covers on the intake.
Sealing all the holes.
Exactly. And as you take each one off, you're looking closely for any signs of corrosion on the parts underneath. Even those dehydrator plugs and the spark plug holes get checked. If the little color indicator looks dodgy, suggests moisture got in.
Uh-huh.
You got to do a really careful check of the inside of that cylinder wall.
Mm.
Sometimes you even have to pull the cylinder off completely to get a good look.
Wow. And are there specific traps for certain engine types, like those big old radial engines?
Yes, good point.
Oh.
Radials have a particular quirk. You have to be really careful about too much of that gooey, corrosion-preventive gunk pooling in the bottom cylinders and intake pipes while it was stored.
Gunk. Pooling. Why is that bad?
Because if you try to turn the engine over with liquid trapped in a cylinder, it can cause what's called hydraulic lock.
Hydrolock. Sounds bad.
It is. The liquid doesn't compress, so something has to give, usually a bent connecting rod. Very bad news.
Yikes. So how do you avoid that?
There are specific procedures. Checking the lower cylinders, maybe using a hand pump to suck out any excess gunk, sometimes even carefully opening an intake valve to let it drain. It's all in the manual.
Right. Always follow the manual. And it's not just the main engine block that needs this treatment, is it? What about all the accessories? The pumps, the generator?
Absolutely. An engine's no good without its support systems. First thing with accessories is check the storage records. How long has it been sitting there?
Why does that matter?
Some accessories actually have manufacturer time limits for storage.
Mm-hmm.
Shelf life, basically. Beyond that, they're considered potentially unreliable and have to be replaced, even if they look okay. And any accessory you do plan to reuse needs a really thorough inspection, general condition, cleanliness, corrosion, anywhere on moving parts. And importantly, if the old engine failed internally, certain accessories, especially in the oil system, might need automatic replacement because they could be contaminated with metal bits from the failure. You don't want that getting into your nice new engine.
Right, contaminating the new one. Makes sense. So super clean, super careful inspection for everything. Engine and accessories. Okay, let's say the replacement engine is prepped, ready to rock. What about the plane itself? What needs doing there before the new engine goes in?
The nacelle on the aircraft needs just as much attention. Usually starts with a really good cleaning of the whole area.
Get rid of any grime or oil.
Exactly. Then you inspect the framework inside the nacelle looking for any distortion, corrosion, cracks. They might use dye penetrant tests to find tiny surface cracks you would normally see.
Like a fluorescent dye.
Yeah, often. The sheet metal cowling parts get checked too, any riveted plates, and even the big bolts holding the engine mount to the aircraft structure get inspected. Sometimes magnetic particle inspection for hidden flaws. And you check the bolt holes for stretching or wear.
Wow, checking the holes themselves. Detailed stuff. What about all the wires and pipes running through there?
They all get a close look. Electrical wires. Check for insulation breaks, chafing where they might rub, make sure connectors are tight and clean. Fluid tubes. Look for dents, nicks, corrosion, any signs of fatigue like weird bends. Flexible hoses. Check for cracking on the outside, peeling, or those deep clamp marks called cold flow that weaken the hose.
Cold flow. All right.
Any of that might mean replacement. Even the mechanical control rods get checked for nicks or corrosion that could weaken them. And on older planes with cables.
Pulleys and cables.
Yeah, check the pulleys move freely, no excessive wear. Check the cables for rust, broken strands.
And you mentioned bonding earlier. The electrical grounding straps.
Precisely. Check all bonding connections. They're frayed, loose, corroded. And you actually measure their electrical resistance to make sure it's low enough within spec for proper grounding.
Okay.
Then the exhaust system, check it's secure, no cracks, no bad corrosion. And finally, all the air ducts inside the nacelle, check for dents that block airflow. Check the anti-chafing strips are okay.
So it's really a top-to-bottom inspection of the whole nacelle area before the new engine goes anywhere near it. What about the oil system parts that stay on the aircraft? Like the oil tank, the cooler?
Good question. If the old engine was just removed for reaching its TBO, a normal lifespan change, then usually just flushing the aircraft's oil system components, the tank, cooler lines, is enough. But if the old engine failed internally, maybe through some metal.
Ah, contamination risk again.
Exactly. Then components like the oil tank, the oil cooler, the pressure regulator valve. They often need to be removed for a much more thorough cleaning, maybe even sent out for overhaul. And lines go into things like the vacuum pump, the prop governor, the feathering pump if it's oil-driven. They all need careful checking and maybe cleaning or replacement too. Don't want any debris hiding in the system.
Okay, makes perfect sense. So replacement engine is ready. Aircraft nacelle is inspected and clean. Now we get to the actual removal of the old engine. What are the absolute first steps?
Safety prep.
Safety is always job number one. First thing, magneto switch OFFA if it's a piston engine.
Ignition off.
Right. Then, close all fuel selectors, fuel shut-off valves. You might need battery power on for a second to close electric solenoid valves.
Okay.
But once they're closed, disconnect the battery completely, prevents accidental starts, electrical sparks.
Oh, cool.
Then make sure fire extinguishers are right there, ready to go, seals intact, chock the aircraft wheels securely. And for tricycle gear planes, it's usually smart to put a support under the tail. Why the tail support?
Because when you take that heavy engine off the front, the plane's balance changes drastically. It could easily tip back onto its tail without support.
Ah, okay. Balance shift.
Yeah. And lastly, often they'll deflate the landing gear struts a bit just to make the plane sit lower and more stable.
Right. So, safe working area, plane secured. What's next? Getting access.
Yep. Remove the engine cowling panels and inspect them as you take them off. Then the propeller comes off.
Propeller off. Gives you room to work.
Room to work, plus the prop needs its own inspection or maybe repair anyway. Before you start disconnecting things, get a big drip pan underneath to catch spills, and have containers ready for draining the engine oil or that preservative gunk if it was stored.
Where does the oil drain from?
Usually the main subplug, sometimes the oil cooler has a drain, maybe a low point and a return line. Drain it all, then put the plugs back in, usually with new seals or washers.
Okay, fluids handled. Then it's time for
The wires. Yep, electrical disconnects usually happens at or near the firewall. If you're leaving some accessories on the plane, you might disconnect starter or generator leads right at the component.
safety first with electricity.
Always. Good practice is disconnect magneto leads first on piston engines and make sure they're grounded. Stops any chance of accidental firing. Most connections use those standard AN or MS connectors.
The round metal ones with the screw collar?
That's them. They often have safety wire on the collar. Carefully cut and remove all the broken wire bits. Then wrap the open ends of the connectors with good moisture-proof tape. Protects them.
Keeps dirt and moisture out.
Right. And any loose cables or conduits, coil them up neatly and tie them securely to the airframe so they don't flop around and get tangled during the lift.
Got it. Electricity sorted? What about the mechanical links? Throttle, mixture controls?
Those usually connect via rods and cables. You'll disconnect them, often by undoing turnbuckles on cable ends. On piston engines, you see control rods linked to bell cranks with things like clevis pins, secured with castle nuts and cotter pins.
Lots of little bits of hardware.
Yeah. And a good tip, when you disconnect a linkage, put the nut and bolt back in the hole temporarily. Stops you losing them.
Smart. Simple but smart.
And make sure any disconnected rods are either removed completely or tied back securely so they don't swing around and get bent when the engine starts moving.
Okay, mechanical links undone. How about all the plumbing? Fuel lines, oil lines, hydraulic lines.
Those can be flexible hoses or rigid metal tubes, sometimes joined with clamps. High-pressure stuff is often stainless steel. Disconnects at the firewall could be threaded fittings, quick disconnects with built-in check valves.
Quick disconnects sound handy. Less spillage.
Yeah, they help minimize fluid loss. If you have metal tube joined by a short rubber hose, you loosen the clamps, carefully slide the hose off. Always have containers ready to catch draining fluid.
And plug the open lines.
Immediately. As soon as the line is disconnected, plug it or tape it securely. Stops leaks, keeps dirt out. Crucial.
And I guess there are other things too, like air ducts, exhaust pipes.
Yep, exactly. Air intake ducts, exhaust system components, they all need disconnecting. The key is a final, thorough visual check. Make absolutely sure everything electrical, mechanical fluid is totally disconnected and free before you even think about attaching the hoist. Don't want anything snagging halfway out. Precisely. That's how things get damaged or people get hurt. Double check everything is clear.
All right, everything's disconnected. Now for the main event. Actually lifting the engine out.
Right. Now, if you're pulling a whole QBCA unit, the engine mat usually comes with it. If it's just the bare engine, the mount stays on the firewall.
Okay.
First step is attaching a certified engine hoisting sling to the proper lift points on the engine. Always inspect that sling carefully. First check for wear, damage. And make sure the hoist itself has enough capacity for the engine's weight, considering its center of gravity too.
Gotta lift it balanced.
Exactly. And lift smoothly, controlled. Whether it's a manual chain hoist or a power hoist, slow and steady wins the race. Be extra careful with power hoists.
Safety checks before lifting.
Absolutely. Double check those tail supports, and wheel chocks are still solid. Sometimes they attach guide ropes to the engine.
Guide ropes.
Yeah, so people on the ground can help control any swinging as it comes up. Once the hoist is attached and just taking the flak, then you start removing the engine mount, bolts, or nuts.
In a specific order.
Always follow the manufacturer's sequence. It distributes the stress properly. As you get to the last few bolts, Have people ready to steady the engine, maybe using those guide ropes. If it's bolts, make sure the hoist is taking the weight before pulling the last ones.
Okay.
Once all the attachments are off, gently, carefully ease the engine forward away from the mount. If it binds up anywhere,
Don't force it.
never force it. Stop.
Yeah.
Maneuver the engine slightly with the hoist until it clears. Check the manual if you're unsure. Once it's completely free,
Lower it down.
carefully lower it onto a proper engine stand and bolt it down securely. That stand holds it while you maybe take off more accessories or do other work.
Okay, old engine out, safely on its stand. Now, putting the new one in, is it just the exact reverse, or are there key things to watch out for during installation?
It's mostly the reverse, yeah, but with some important points.
Yeah.
First, get the new engine on its stand positioned close to the nacelle opening.
Makes sense. Minimize travel distance.
Right. Attach the sling, connect the hoist, lift it just enough to take the weight, then unbolt it from the stand, lift it clear, and move the stand and hoist carefully to get good access to the nacelle.
Steady hands required.
Very steady hands and good communication between everyone involved. Then slowly, precisely, guide the engine into position inside the nacelle. You're lining up the mounting holes on the engine with the holes on the aircraft mount, plus getting exhaust parts roughly aligned.
Okay.
Once it's in place, insert all the mounting bolts. Make sure you're using the right bolts, correct size, type, everything. Never substitute hardware here.
Critical fact.
Absolutely. Start tightening the nuts, but keep the hoist supporting the engine's weight initially. Helps maintain alignment. Tighten them to the specified torque value, following the manufacturer's sequence again.
Tightening sequence again. Important.
Ensures even load distribution. Once they're all torqued, safety them properly, lock washers, cotter pins, safety wire, whatever's required. Then you can remove the sling and hoist. And don't forget to reconnect any bonding straps across the mounts if they were removed.
Okay, engine physically mounted. But that's just the start of reassembly, right? Lots to reconnect.
Oh yeah, now you've got to reconnect everything, ducts, wires, controls, lines. It's a big job.
Is there a standard order for reconnecting everything, or best practices?
There's no single universal order, but experienced shops will use detailed checklists, tailored to the specific aircraft. Following a checklist is definitely best practice. Prevents missing things.
Right, checklists are good. What about connecting things like air ducts?
For ducts, the main thing is getting a tight, leak-free fit. Especially pressurized air ducts. Some might even need a pressure test after installation. Clean or replace air filters according to the book.
And the exhaust system. Seems critical to get that right.
Very critical. Hot, dangerous gases. You need careful alignment, use the right hardware, tighten clamps progressively for a good seal. Sometimes gently tapping the clamps helps them seat. If there are ball joints, check they have the right clearance for thermal expansion.
Okay, hoses and tubes.
Inspect hose clamps again, make sure they work smoothly, no defects. Support hoses properly with rubber-lined clamps to stop chafing. For metal tube fittings, clean threads, use the right sealant or lube specified in the manual.
Electrical connections.
Clean and secure. Replace any lock washers or safety wire that came off. Anchor conduits properly, make sure bonding is good. And finally, all the mechanical engine controls, throttle, mixture, prop, need accurate adjustment. Again, follow the specific procedure for that aircraft model.
Let's talk about those control adjustments. You gave an example earlier for a piston engine throttle. Can you recap the basic idea?
Sure. The general idea is you set a known starting point. For the throttle, maybe ensure the valve is fully closed by adjusting a stop screw. Then you might lock something, like a cable drum, in a reference position. Then adjust the length of a connecting rod to line up correctly. Reconnect it. If it's cables, you loosen turnbuckles, set the cockpit lever to its reference position like idle, maybe lock it with rigging pins.
Rigging pins, temporary locks.
Yeah, they hold things in the right place for adjustment. Then you use a tensionometer, a special gauge, to set the correct cable tension, again with everything pinned.
Okay, tension set.
Then you often adjust for a little bit of cushion at the ends of the travel, full open and fully closed. Just a tiny bit of slack, adjusted equally on the turnbuckles, stops things binding at the limits.
Makes sense. So set a length, set tension, check the cushion.
That's the basic principle for most mechanical controls. And on multi-engine planes, getting that cushion equal on all engines is vital for smooth, synchronized operation.
What about other airflow things? Like cowl flaps or oil cooler doors? How are they adjusted?
Cowl flaps control cooling air, right? So they need adjusting to open and close to the angles specified by the manufacturer. If there are cockpit position indicators, you check they match the actual flap position.
Got it. And oil cooler doors.
Similar idea. Ensure they open and close fully as commanded. Sometimes that involves setting limit switches to tell the system when the door is fully open or fully closed.
Okay. And after the engine's in, controls connected, the propeller goes back on. Any special steps there?
Yeah, before installing the prop, check the torque on its thrust bearing retaining nut, make sure it's right.
Yeah.
Lubricate the shaft if needed, using the approved stuff. Then connect the prop governor controls and any anti-icing system parts, following the specific manual for that propagating combo.
All right. Engine in, connected, adjusted, prop on. What's the big next phase before it flies again? Testing prep.
Exactly, preparing for ground runs and flight tests. And a really vital first step here is pre-oiling the engine.
Pre-oiling. Why?
Because if an engine's brand new or been sitting, the oil can drain away from bearings. Starting it dry, even for a second, can cause major damage right away. Scuffed bearings, worse.
Ah, okay. So you force oil through before the first start.
Precisely. Force oil through the whole system. There are a few ways. One common method is disconnecting the oil pump inlet, hooking up an external pre-oiler tank.
A separate tank.
Yeah, pressurized with air. It pushes oil through the engine while you slowly turn it over by hand or with the starter until you see oil coming out somewhere specific, like the prop governor pad.
Okay. Other ways?
You could use a motor-driven external pump, or you can sometimes use the engine's own oil pump. You crank the engine with the starter, but crucially, mixture OFS, fuel off-F, ignition OF, throttles open until you see oil pressure register on the gauge.
Cranking without starting it.
Right. Once it's pre-oiled, reinstall spark plugs if they are out, reconnect everything, and it's best to actually start and run the engine within about 4 hours after pre-oiling. Otherwise, you might need to do it again.
Got it. Pre-oiling is critical. What about the fuel system? Getting it ready?
Yeah, you need to bleed the fuel system, get rid of any trapped air from the installation, and also flush out any leftover preservative oil, especially from sensitive bits like fuel controls.
How do you bleed it?
Typically, find a drain plug downstream, often on the fuel control unit. Attach a hose, run it to a container, set the fuel controls to allow flight, open the main fuel valves, tank selectors, turn on the electric boost pump.
And just pump fuel through.
Yeah, until you get a steady stream of clean fuel coming out the drain hose. No air bubbles, no discoloration from preservative oil. Once it's clear, turn everything off, put the plug back, safety it, system bled.
Okay. And you mentioned checking the propeller before, during, and after the ground run. What are you looking for?
Before starting, visual check for damage. Check mounting bolt torque. During the run, listen and feel for vibrations. Look for any oil or grease leaks from the hub. After shutdown, another visual check. Maybe retorque the bolts if the manual says so. For props with electric pitch change, you can often check that function before starting. For oil pressure types, you check pitch change after the engine's warmed up. Watch the RPM change. Check feathering if it has it.
Makes sense. So after the engine's been run for a bit on the ground, what other checks or tweaks are needed before flying?
After the ground run, and definitely after the first test flight, there are more checks. You'll probably need to fine-tune fuel pressure, oil pressure to get them right in the operating range. Recheck ignition timing, valve clearances on piston engines, idle speed, idle mixture, especially if performance seemed off.
So fine-tuning based on how it ran?
Exactly. And crucially, pull the oil sump plugs and screens again. Look very carefully for any metal particles. Clean the screens thoroughly.
Checking for early wear signs.
Right. Then, a full check of all fluid lines. Again, look for leaks. Make sure all clamps and fittings are tight. Oil hose clamps are particularly important to recheck after heat cycles. And on piston engines, recheck the cylinder-based nuts or screws for torque and safety. Often done again after the first flight, too.
Wow. It really is a continuous process of checking and adjusting. You also mentioned rigging fuel controls and other stuff earlier.
Yeah, proper rigging is vital. That means inspecting all the linkages, bell cranks, rod ends, cable drums, guards for looseness, damage, wear.
Yeah.
When you actually rig things like fuel selectors, power levers, shut-off valves, you absolutely must follow the step-by-step procedure in the specific aircraft maintenance manual. No shortcuts. For cables, set the exact tension specified, usually using those rigging pins again. The pin should slide in and out freely if the rigging's right. Check the power lever has the right amount of cushion at the ends. Make sure indicators on the fuel control line up correctly. Check fuel selectors move fully without restricting flow.
And for those older turbofans with the mechanical controls, cables and rods, you mentioned specific rigging for them too.
Absolutely. Those complex systems, bell cranks, rods, drums, pulleys, cables, need careful adjustment so the cockpit lever movement translates accurately to the engine fuel control. And on multi-engine planes, they need to be synchronized.
So both levers do the same thing at the same time.
Exactly. Anytime you change an engine or fuel control on those older types, you have to re-rig the whole system from the pylon back to the engine. Check the cockpit lever moves freely first, then make adjustments at the engine end. Move the lever through its full range, check for binding, then lock everything down securely. Lock nuts, cotter pins, safety wire.
And the fuel control unit itself on those older ones often needs trimming.
Yes, that's right. Those hydromechanical fuel controls need fine-tuning or trimming to get the performance right, especially after replacement or if max thrust seems low.
How is that done?
There are usually adjustment screws on the unit itself. One for idle RPM, often labeled INC, idle E. Another for max thrust, maybe INC max. You do this with the engine running, ideally into a headwind, avoiding icing conditions.
Need specific tools.
Often a special trim gauge connected to turbine discharge pressure. You compare the reading to charts in the manual, compensating for temperature and pressure, and adjust the screws to get the right value. If the plane has an EPR gauge, engine pressure ratio, you might use that as the reference.
And newer electronic controls.
They still need trim checks, but it's usually comparing parameters like idle speeds, bleed settings, EPR, against target values from charts based on current temp and pressure. Fewer physical screws to turn, more verifying digital targets.
Okay, we've hit piston engines and turbofans pretty hard. What about turboprops? Is the removal installation similar to jets?
Mostly, yes, especially if it's a QECA approach. The process is very similar to a turbojet QECA. The main differences are obviously related to the propeller and its gearbox and controls.
So extra connections for the prop system.
Right. You'll still disconnect thermocouples, fluid lines, close valves, plug lines, bleed air ducts, electrics, vents, fuel hydraulic lines, power lever, prop controls. Use the QDCA lift points, sling, hoist, accounting for the different center of gravity with the prop gearbox. Remove mount bolts, double-check all disconnects, move it forward, lower it onto a turboprop QECA stand.
Installation is the reverse.
Pretty much. Pay close attention to using new O-rings on fluid lines, follow all torque limits strictly. Then a thorough post-installation run-up is essential, checking the engine and all related systems against the manufacturer's test procedures.
And helicopters.
Very.
Any unique things there, especially with piston engines or QECAs?
Yeah, helicopter engines often sit differently, maybe facing aft, maybe angled upward significantly.
Right.
They definitely use QECAs too. A helicopter QECA includes the engine, mount, accessories, controls, all the systems, fuel, lube, ignition, cooling, plus maybe the clutch and cooling fan assembly.
How do they come out?
Similar principles. Preserve if needed, shut off fuel, grain oil, make all the disconnects. Attach a sling, might need a higher capacity, maybe 2 tons. Apply slight lift. Often loosen lower mount bolts before upper ones. Remove any sway braces, then upper bolts, then lower. Lift the QECA out, place it on a work stand.
Installation is reverse again, with extra checks.
Reverse, yeah.
Yeah.
Always check the manuals for part interchangeability of swapping components. Meticulously follow rigging instructions for throttle, mixture, cable tensions. Then a normal engine run-in per the manual, followed by a flight test after installation and control adjustments.
Engine mounts are obviously vital, holding the whole thing on. What different types are common?
For piston engines, often welded steel tube structures, a main ring, V-struts, attachment fittings bolting to the firewall. Use a special heat-treated bolt supercritical. They handle weight and all the flight stresses, including twisting forces.
Right.
Many use dynamic mounts, maybe 4 points on the ring. The engine attaches to the ring via vibration isolators. A common type is the dynafocal mount angled rubber pads pointing toward the engine's center of gravity. Helps damp vibration directionally. Other shock mounts use rubber, and steel rubber supports the load normally. Metal snubbers limit excessive movement.
And for the big turbofans?
Usually stainless steel mounts, very strong, handling weight and massive thrust loads, typically 3 points, 2 forward, 1 rear. They often use more advanced vibration isolation mounts.
How do those work?
The forward ones handle vertical, side, and thrust loads, but allow for thermal expansion. The aft ones handle vertical and side loads, also allowing for thermal growth without stressing flanges. The isolators themselves have resilient material, like special rubber, inside a metal case to dampen vibration. Importantly, they're designed so even if the rubber fails, the metal parts still support the engine. Fail-safe design.
Okay, finally, let's touch on preservation and storage. Why is it so crucial to preserve an engine that's not being used?
Main reason, corrosion. Simple as that. When an engine sits idle, moisture from the air plus leftover combustion byproducts inside can attack the metal surfaces. Rust, pitting, bad news.
Especially near the coast or in humid places?
Exactly. Humidity is the enemy. Also, an engine run hard for short periods might get a thin protective varnish layer, but that's not enough for proper long-term storage.
So what do they use to protect them? Special oils?
Primarily, yes. Corrosion preventive compounds, usually petroleum-based, they form a waxy film. Different types exist. Lighter mixtures mixed with engine oil for short-term inactivity, maybe under 30 days. Heavier stuff for longer storage, sometimes used for dipping parts.
How do you get it off?
Usually commercial solvents or kerosene when it's time to return to service. But these compounds do break down eventually, so periodic checks are needed.
And those little bags you see? Desiccants?
Right, desiccants like silica gel, they absorb moisture directly from the air. You find them in bags placed inside engine cavities and also inside special dehydrator plugs that screw into spark plug holes.
The ones with the color indicator?
Yeah, often cobalt chloride. Blue usually means dry. Pink means high humidity. Time to check things. Keep the desiccant bags sealed until use, otherwise they just absorb moisture from the room air.
Okay, so how do you actually do the preservation on a piston engine and then get it back into service?
Preservation usually starts with running the engine to warm it up, drain the normal oil, refill with the specified preservative oil mix, run it again for at least an hour to circulate that stuff everywhere. Prop safety is vital here.
Then shut it down.
Shut down. Pull the top spark plugs. Spray preservative mix into each cylinder, usually with the piston at bottom dead center. Then, don't turn the crank. Spray more preservative in with the crank stationary to coat the walls.
Yeah.
Put a big tag on, do not turn crankshaft. Install dehydrator plugs in the spark plug holes. Seal up the exhaust ports with preservative and cover plates. Seal the intake manifold, maybe wire the throttle open and seal the air inlet, or seal the mounting pad if the carb is off, often with silica gel inside. Coat the prop shaft. Seal every other opening breathers, accessory pads with plates or moisture-proof tape. Often remove certain accessories like starters, generators, pumps for separate preservation.
And bringing it back.
Remove all seals, desiccants, pull dehydrator plugs, spark plugs, drain the preservative oil, new drain plug seal, new oil filter, fill with fresh service oil. Safety precautions first. Mags off grounded, throttle closed, mixture cut off, brakes set chocked, stay clear of the prop arc. Then, carefully turn the prop by hand several times. Make sure no hydrolock helps spread the fresh oil.
Then install plugs, start it up.
Service and install plugs leads. Clean and inspect everything. Fix any issues, normal start. Operational test per the manual, fix anything found there. Then usually a test flight by qualified crew, following airframe manufacturer procedures. Fix anything found on the test flight before it's officially back in service. Often change the oil and filter again after the first 25 hours too.
What about shipping these things, those big containers?
Yeah, specialized containers. Could be plastic foil envelopes inside wooden crates or pressurized metal containers. Engine gets bolted to a mounting plate inside. If using an envelope, put silica gel inside before sealing it. Vacuum helps. Then heat seal it shut. Inventory check. Humidity indicator visible through a window. Secure the lid. Mark the container with ID, preservation date, status.
Metal containers are different.
Usually need more silica gel because they're bigger and often have vented plugs in the engine. They have a rubber seal on the lid. Inspect that. They're reusable. After sealing, they're often pressurized with dry air. Check for leaks using the pressure gauge. All paperwork inside or attached outside.
How often do stored engines get checked?
On a schedule. Wooden case envelope. Check humidity indicator maybe every 30 days, or 90 if undisturbed. Metal container. Check pressure humidity maybe every 180 days. If humidity is too high in a wooden case, replace desiccants. If dehydrator plugs show moisture, might need to respray cylinders. If metal container pressure drops, repressurize with dry air. If humidity is bad in a metal container, engine needs represervation.
Wow. This has been incredibly detailed. We've really covered the waterfront, why engines come out, the step-by-step for swaps on different types, firewalls, mounts, preservation. It's just staggering. The complexity and the absolute need for following procedures to the letter really highlights the safety focus in aviation.
It really does. And it's funny, you see a plane takeoff seems so routine, but behind that, like we've discussed, there's just this immense depth of technical knowledge and rigorous process. Swapping an engine is a perfect example.
Absolutely. It makes you wonder, doesn't it? Considering all this detail for just one aspect of maintenance, what other simple things in aviation hide that same kind of deep technical world?
Yeah.
Maybe avionics systems or hydraulics. Could be another fascinating deep dive sometime.
Could be. There's always more to learn.
For sure. Well, thanks so much for walking us through all that today. Really insightful stuff. And thanks everyone for joining us on the deep dive.